something cold drifts far beyond Neptune, a distant world made of ice and rock, a place where sunlight is so weak it looks like twilight. This world is called Orcus. For a long time, it was just another faint point of light in the darkness of the Kuiper Belt, a frozen object among thousands of others orbiting the Sun at unimaginable distances. But astronomers noticed something strange. Orcus moves through space in a way that mirrors Pluto. Its orbit follows a similar path, almost like a reflection across the solar system. Because of this, scientists sometimes call Orcus Pluto's twin, a distant sibling of the famous dwarf planet. But Orcus hides more than just a curious orbit. It has a large moon called Vanth. And together, they travel through the outer solar system like a quiet binary world, locked in a slow gravitational dance, far from the warmth of the Sun, far from the inner planets. And yet, this silent world may hold secrets about how the outer solar system formed billions of years ago, secrets frozen in ice since the birth of the planets. Tonight, we travel to that distant frontier to explore one of the strangest objects beyond Neptune, Orcus, Pluto's strange twin. And if you enjoy exploring the quiet mysteries of deep space, consider subscribing to Theories Before Sleep, where we uncover the universe one calm story at a time. In the early years of the 21st century, astronomers were beginning to realize something extraordinary. The solar system was far larger and more complex than anyone had imagined only a few decades earlier. Beyond Neptune, far from the familiar planets, a vast region filled with icy worlds stretches into darkness. This region is known as the Kuiper Belt. For most of human history, this distant frontier was invisible to us. The objects there are incredibly faint. They receive only a tiny fraction of the sunlight that reaches Earth, and they move slowly against the background of distant stars. Detecting them requires powerful telescopes and patient observation. But by the late 1990s and early 2000s, astronomers had begun to systematically search the outer solar system. Large digital sky surveys scanned the night sky, looking for tiny points of light that moved slightly between observations. Those faint moving dots were often distant objects orbiting the Sun far beyond Neptune. Many of them were small, some were surprisingly large, and a few turned out to be worlds comparable in size to Pluto. It was during one of these surveys that Orcus was discovered. The discovery occurred on February 17, 2004. Astronomers Michael Brown, Chad Trujillo, and David Rabinowitz were examining images taken at the Palomar Observatory in California. Their search was focused on identifying large Kuiper Belt objects, distant bodies that might rival Pluto in size. While analyzing the data, they noticed something interesting. A faint point of light appeared to shift position between two images of the same region of sky. At first glance, it was easy to overlook. The object was extremely dim, barely distinguishable from background stars. But careful measurements confirmed it was moving, slowly, steadily, exactly as a distant object orbiting the Sun would. Further observations quickly confirmed that this object was far beyond Neptune. Its distance from the Sun was roughly 39 astronomical units, meaning it was about 39 times farther from the Sun than Earth. At that distance, sunlight takes more than 5 hours to reach the object. the team realized they had found something significant: a new world in the Kuiper Belt. And not just a small fragment of ice, but a large body hundreds of kilometers across. Soon after its discovery, astronomers began calculating its orbit. The results were surprising. Most Kuiper Belt objects follow irregular paths around the Sun. Their orbits can be tilted, stretched, or influenced by the gravity of Neptune in complex ways. But this new object had an orbit that seemed strangely familiar. Its path around the Sun had nearly the same orbital resonance as Pluto. Pluto completes 2 orbits for every 3 orbits of Neptune. Orcus does exactly the same. Both worlds are locked in the same gravitational rhythm with Neptune. But there was something even stranger. The orbit of Orcus was almost a mirror image of Pluto's orbit. When Pluto is closest to the Sun, Orcus is farthest away. When Pluto is on one side of the solar system, Orcus is often found on the opposite side. Their paths through space are almost symmetrical. Because of this remarkable relationship, astronomers began referring to Orcus as the anti-Pluto, not because it is the opposite of Pluto in size or composition, but because its orbit appears to mirror Pluto's motion across the solar system. This orbital symmetry fascinated researchers. It suggested that Orcus and Pluto may share a related history. Both objects are part of a special group of Kuiper Belt objects called Plutinos. These bodies share Pluto's 2 to 3 orbital resonance with Neptune, meaning their gravitational interactions with the giant planet keep their orbits stable over long periods of time. The discovery of Orcus helped scientists understand how Neptune shaped the outer solar system. Billions of years ago, when the giant planets were still migrating through space, Neptune moved outward from the Sun. As it did, its gravity captured certain icy objects into resonant orbits. Pluto was one of them. Orcus appears to be another. But Orcus also had its own surprises waiting to be discovered. Shortly after its discovery, astronomers noticed that the brightness of the object changed slightly over time. These variations hinted that something else might be present. A companion, a moon. Further observations eventually confirmed it. Orcus was not traveling through space alone. It had a large moon orbiting it. That moon would soon be given the name Vanth. And the discovery of Vanth would reveal something even more unusual about this distant world. Because together, Orcus and its moon form one of the most intriguing binary systems in the Kuiper Belt. But to understand why this system is so unusual, we must first look more closely at the dwarf planet itself. How large is Orcus? What is it made of? And what does its frozen surface look like in the distant twilight of the outer solar system? Those questions lead us deeper into the story of Pluto's strange twin. From the moment Orcus was discovered, one question immediately followed. How big is it? That may sound simple, but in the outer solar system, size is one of the hardest things to measure. Orcus is incredibly far away. Even with powerful telescopes, it does not appear as a detailed world with visible mountains, plains, or craters. It appears as a tiny point of light, faint against the darkness of the Kuiper Belt. And when an object is that distant, brightness can be misleading. A small object with a very reflective surface can appear bright. A large object with a dark surface can appear dim. So when astronomers first saw Orcus, they could not determine its size from brightness alone. They needed something more. They needed to know how much light the object reflected and how much of that reflected light came from its surface area. This is where careful observation became essential. By combining visible light measurements with thermal observations, how much heat the object emits, astronomers could begin to estimate both its size and its reflectivity. A cold object in the outer solar system absorbs a tiny amount of sunlight and then releases that energy slowly as heat. Measuring that heat helps reveal how large the object must be. Over time, those measurements produced a clearer picture. Orcus is not as large as Pluto. It is not large enough to dominate the Kuiper Belt in the same way Pluto once seemed to. But it is still substantial. Its diameter is now estimated to be roughly 900 kilometers, making it one of the larger known objects beyond Neptune. That places it in an interesting category, too large to be dismissed as just another icy fragment, but still small compared to the largest dwarf planets of the outer solar system. To understand its scale, it helps to compare it with other familiar worlds. Pluto is about 2,377 kilometers across. The Moon is about 3,474 kilometers across. Ceres, the dwarf planet in the asteroid belt, is about 940 kilometers wide. That means Orcus is actually quite close in size to Ceres. And yet, despite that similarity, the two worlds could hardly be more different. Ceres exists in the warmer inner solar system, among rocks and asteroids. Orcus exists in the deep cold beyond Neptune, among frozen bodies that preserve the earliest conditions of planetary formation. Its size alone makes it important. At around 900 kilometers across, Orcus is large enough for its own gravity to shape it into a roughly spherical form. And that matters because one of the defining features of dwarf planets is that they are massive enough to become rounded under their own gravity. This means Orcus is not just a chunk of debris. It is a world, a complete body with enough gravity to pull itself into balance. But that balance is not perfect. Unlike larger planets, which become more fully spherical, smaller bodies like Orcus may still preserve subtle irregularities. The exact shape of Orcus is difficult to determine from Earth, but it is likely close to spherical, perhaps slightly elongated, depending on its rotational history and its interaction with Vanth, its large moon. And that interaction is more important than it may first appear, because Orcus does not exist in isolation. Its moon is large enough and close enough to influence how the system behaves. The gravitational relationship between Orcus and Vanth may have altered the rotation of the dwarf planet over time, slowing it down and possibly shaping its orientation. But before we get to the moon, we need to stay with Orcus itself, because size is only one part of the puzzle. The next question is mass. How heavy is this distant world? Again, measuring that directly is not easy. But once Vanth was discovered, astronomers gained a major advantage. By watching the moon orbit Orcus, they could calculate the total mass of the system. The speed of Vanth's orbit and its distance from Orcus reveal how much gravity is present, and gravity tells us mass. These calculations showed that Orcus is much less massive than Pluto, which is expected given its smaller size. But more interestingly, the mass also allows scientists to estimate the dwarf planet's density. Density is one of the most useful clues we can get about a distant object because it tells us something about what the inside might be made of. If Orcus were composed almost entirely of water ice, its density would be relatively low. If it contained much more rock, its density would be higher. The measurements suggest that Orcus has a mixed composition, part ice, part rock. It is not a pure icy snowball, but neither is it a rocky body with only a thin frost on its surface. This mixture is exactly what astronomers would expect from a large Kuiper Belt object that formed in the outer solar system. In that distant region, temperatures were cold enough for volatile materials, water, methane, ammonia, and other ices to remain stable. At the same time, rocky material from the protoplanetary disk was still present. Worlds forming there would naturally become mixtures of both. And this mixed composition has profound consequences. It means Orcus is not just a frozen shell. It may have had enough internal heat in the past to partially separate into layers, with heavier rocky material sinking inward and lighter ice rising toward the surface. That possibility opens the door to a much deeper story about the interior of this world. But even before we go beneath the surface, there is another physical property worth considering: color. Orcus does not appear bright white like freshwater ice, nor does it look extremely dark like some of the reddest and most heavily irradiated objects in the Kuiper Belt. Its color is more subtle, slightly neutral, slightly gray, a distant, muted world. This tells astronomers something important about what covers the surface. Worlds in the outer solar system are constantly altered by radiation. Ultraviolet light from the sun, cosmic rays, and charged particles slowly modify the chemistry of the surface, turning simple ices into darker and often redder compounds over time. Some Kuiper Belt objects become deeply reddish because of these processes. Orcus does not seem to belong fully to that category. Its more neutral appearance suggests that the surface may contain fresh ice in some regions, or at least that its chemistry differs from some of the redder worlds farther out. That idea becomes even more interesting when spectral observations are added to the story. By analyzing the wavelengths of light reflected from Orcus, astronomers can identify some of the molecules on its surface. Those observations reveal signs of water ice, and perhaps something more. There is evidence suggesting the presence of ammonia compounds, or ammonia hydrates, materials that are especially interesting because they do not remain stable forever on the surface. Radiation gradually destroys or alters them. So if ammonia-related signatures are truly present, they may indicate that the surface has been refreshed at some point in the relatively recent past. That raises a startling possibility for a world so distant and cold. Orcus may not be completely geologically dead, not active in the dramatic sense of volcanoes or geysers erupting into space, but perhaps active enough in the past to expose newer material from below. And that transforms the picture. What began as a simple measurement of size becomes something much more intriguing. A rounded world, roughly 900 kilometers across, massive enough to be a dwarf planet, dense enough to suggest a mixture of rock and ice, bright enough and chemically interesting enough to hint at a more complex history than its distance from the sun would suggest. But perhaps The most fascinating part of all this is how difficult it is to truly know Orcus. Even now, despite all our measurements, we do not have direct images of its surface. We do not know exactly how rugged it is. We do not know whether it has giant basins, icy plains, ancient fractures, or a crust reshaped by internal processes long ago. We know its dimensions. We know its approximate mass. We know some of its surface chemistry. But the world itself remains unresolved. A dwarf planet reduced, from Earth's perspective, to a moving point of light carrying hidden complexity across billions of kilometers of darkness. And that is what makes Orcus so compelling. It sits at the edge of what we can measure, just close enough for us to begin understanding it, just distant enough to remain mysterious. But size and composition are only the beginning, because the real reason Orcus earned its strange reputation lies not in its dimensions, but in the path it follows around the sun. A path so unusual and so strangely connected to Pluto that it transformed Orcus from just another distant object into one of the most fascinating worlds in the outer solar system. Long before Orcus was discovered, astronomers already knew that Pluto followed one of the most unusual orbits in the solar system. Unlike the 8 major planets, which move around the Sun in relatively flat, circular paths, Pluto travels along a highly tilted and stretched orbit. At times, it comes closer to the Sun than Neptune, and at other times, it drifts far beyond it. Yet Pluto never collides with Neptune. This strange stability is not a coincidence. It exists because Pluto is locked into a precise orbital resonance with Neptune. For every 2 orbits Pluto completes, Neptune completes 3. This gravitational rhythm keeps the 2 worlds from ever approaching too closely. Neptune's gravity gently guides Pluto's motion, maintaining a delicate cosmic balance that has lasted for billions of years. For decades, Pluto was thought to be unique. But as astronomers explored the Kuiper Belt, they began discovering other objects trapped in similar resonances. These worlds, known as Plutinos, share Pluto's 2 to 3 resonance with Neptune. Orcus belongs to this group. But Orcus does not simply share Pluto's resonance. Its orbit is something far stranger. When scientists calculated the exact shape and orientation of Orcus's orbit, they noticed a remarkable pattern. The orbit looked almost like Pluto's reflection in a mirror. Both objects travel in elongated paths around the Sun. Both are tilted relative to the plane of the solar system. Both are locked into the same resonance with Neptune, but their positions in space are reversed. When Pluto is near the point in its orbit closest to the Sun, Orcus tends to be near the farthest point of its own orbit. When Pluto moves through one region of the outer solar system, Orcus is often found in the opposite direction. Their motions appear synchronized in a way that feels almost choreographed. Because of this, astronomers sometimes describe Orcus as Pluto's anti-aligned twin. Not identical, not physically connected, but dynamically linked through the structure of their orbits. To understand why this happens, we need to look back billions of years to the early history of the solar system. When the planets first formed, their orbits were not exactly the same as they are today. The giant planets, Jupiter, Saturn, Uranus, and Neptune, migrated through space as they interacted with leftover debris from the formation of the solar system. As they moved, their gravity reshaped the architecture of the outer planetary system. Neptune, in particular, played a crucial role. As it slowly migrated outward, its gravitational influence swept through the Kuiper Belt. Some objects were scattered away, others were ejected entirely from the solar system. But a few were captured into resonant orbits where Neptune's gravity repeatedly nudged them in stable patterns. Pluto was one of those captured objects. Orcus appears to be another. Yet the mirrored orientation of their orbits suggests something even more intriguing. It hints that the capture process may have produced paired orbital structures. Imagine Neptune migrating outward through a cloud of icy bodies. As its gravity reshapes the region, some objects fall into resonances ahead of Neptune's motion, while others fall into resonances behind it. Over time, these objects settle into stable configurations that can last for billions of years. Pluto and Orcus may represent two such configurations, two objects locked into the same resonance, but occupying opposite phases of the orbital pattern. This relationship does not mean they interact directly with each other. They are far too distant for that. But their motions remain tied to the same gravitational architecture controlled by Neptune. The result is one of the most elegant orbital relationships known in the outer solar system. A distant dance between three worlds. Neptune provides the rhythm. Pluto follows one step of the pattern. Orcus follows another. And together, they move through space in a synchronized gravitational choreography that repeats every few hundred years. But Orcus's orbit has other interesting features as well. Its orbital period, the time it takes to complete one journey around the Sun, is roughly 247 years. That is almost identical to Pluto's orbital period of about 248 years. From a cosmic perspective, the two worlds take almost exactly the same amount of time to circle the Sun. Yet because their orbits are mirrored, they rarely occupy the same regions of space. This separation helps maintain long-term stability. Without it, gravitational interactions between Pluto, Orcus, and Neptune might gradually destabilize their orbits. Instead, the geometry of the resonance protects them. Their paths remain carefully arranged so that close encounters are avoided. It is a beautiful example of how gravity shapes order from chaos. But Orcus's orbit also tells us something about its origin. Objects that share Pluto's resonance likely formed in similar regions of the early solar system. They may have originated in the same broad disk of icy material that surrounded the young Sun beyond the giant planets. Some of these objects were scattered outward. Some were captured into resonances, and some were flung far away into distant reservoirs like the scattered disk or the Oort cloud. Orcus survived this chaotic period. It settled into a stable orbit that has remained largely unchanged for billions of years. This stability allows scientists to study it as a fossil world, a relic from the era when the solar system was still forming. But the story of Orcus becomes even more interesting when we look closer at the dynamics of its orbit. Unlike many Kuiper Belt objects, which follow highly irregular paths, Orcus's orbit is relatively well behaved. Its eccentricity, the degree to which its orbit stretches into an ellipse, is moderate. Its inclination, the tilt relative to the solar system's main plane, is also significant but not extreme. These characteristics suggest that Orcus has remained in its resonant state for a very long time. Billions of years of orbital stability, billions of years circling the sun in quiet darkness. But there is one more detail that makes Orcus truly fascinating. The position of Orcus relative to Pluto in their shared resonance is so precisely arranged that the two objects effectively avoid each other forever. Their gravitational dance ensures that they are never close at the same time. When Pluto is in a region where Neptune's gravity might strongly influence it, Orcus is somewhere else entirely. And when Orcus approaches that same region centuries later, Pluto has already moved on. It is a celestial choreography designed by gravity itself, and it has worked flawlessly for billions of years. Yet despite this elegant orbital relationship, Orcus is not merely a passive traveler through the Kuiper Belt. It has its own companion, a large moon named Vanth, and the existence of that moon changes everything we thought we understood about Orcus, because the Orcus-Vanth system is not just a dwarf planet with a tiny satellite. It may be something closer to a binary world, two objects of comparable scale locked together in deep space. And the origin of that pair remains one of the most intriguing mysteries in the outer solar system. For a short time after the discovery of Orcus, astronomers believed they were observing a single distant dwarf planet quietly orbiting the sun in the outer solar system. But that picture did not last long. Only a year after Orcus was first identified, new observations revealed something unexpected. Careful analysis of telescope images showed that Orcus was not alone. A second object appeared extremely close to it. At first, it was difficult to confirm. Objects this distant are faint, and the separation between Orcus and the mysterious companion was incredibly small when viewed from Earth. Only the most powerful telescopes could resolve the 2 points of light. But the evidence became undeniable. Orcus had a moon. The discovery was announced in 2005, and the moon was later given the name Vanth. The name comes from Etruscan mythology. In ancient Etruscan belief, Vanth was a winged female figure associated with a journey to the underworld. The name was chosen deliberately to match the theme of Orcus itself, which was named after a Roman god of the underworld. But beyond the mythological connection, the presence of Vanth introduced an entirely new scientific mystery. Because Vanth is not a small moon, it is unusually large compared to the body it orbits. In most dwarf planet systems, the primary object dominates the system. Pluto, for example, has several small moons, but only one, Charon, is large enough to significantly influence Pluto itself. Orcus and Vanth appear to form a similar pair. Vanth's diameter is estimated to be roughly 440 kilometers, about half the size of Orcus itself. That makes it enormous compared to most moons orbiting objects of this scale. The ratio between their sizes immediately caught astronomers' attention. A moon that large suggests that the Orcus system did not form in a simple way. Many small moons in the solar system form when debris from impacts collects into orbit around a larger body. But those moons are usually tiny compared to the primary world. Vanth is different. It is large enough that the system may behave more like a binary pair. To understand this, astronomers studied Vanth's orbit in detail. The moon circles Orcus once every about 9.5 days. Its orbital distance is approximately 9,000 kilometers from the center of Orcus. On human scales, this would seem enormous, but in planetary terms, it is quite close. This tight orbit allowed scientists to calculate the mass of the entire system with much greater accuracy. But the orbit also revealed something else. Vanth's path around Orcus is almost perfectly circular, and its orbital plane is aligned in a way that suggests the system may be tidally locked. In a tidally locked system, the same side of one body always faces the other. Earth's moon is the most familiar example. We always see the same lunar hemisphere because the moon rotates exactly once for every orbit it completes around Earth. In the Orcus-Vanth system, a similar relationship may exist. Orcus rotates slowly enough that it may keep the same face oriented toward Vanth at all times. Vanth, in turn, likely shows only one side to Orcus. If this is true, then the two bodies are gravitationally synchronized, locked together, forever facing each other across the darkness of space. This kind of arrangement usually forms when tidal forces gradually slow the rotation of both bodies over long periods of time. Energy is dissipated as internal friction, and eventually the system settles into a stable configuration where neither body spins freely anymore. But the question remains, how did Vanth form in the first place? There are several possible explanations. One possibility is that Vanth formed from debris after a massive collision. In the early solar system, impacts between large icy bodies were common. If Orcus experienced a collision with another Kuiper Belt object, the impact could have thrown material into orbit. That debris might eventually have clumped together and formed a moon. This is similar to the leading explanation for the formation of Earth's moon. But there is a complication. The color and composition of Vanth appear somewhat different from Orcus itself. Observations suggest that Orcus has a relatively neutral or slightly gray surface color, likely dominated by water ice and other frozen compounds. Vanth, on the other hand, appears somewhat redder. That difference may indicate that the two bodies did not originate from the same material. If they formed from a shared debris cloud, scientists would expect them to have similar surface compositions. Because of this, another possibility has been proposed. Vanth may have been a captured object. In this scenario, Orcus and Vanth formed independently somewhere in the Kuiper Belt. At some point in the distant past, gravitational interactions allowed Orcus to capture Vanth into orbit. Capturing a moon is difficult, but not impossible. It typically requires a mechanism that allows the captured object to lose energy, perhaps through interactions with other nearby bodies or through tidal forces during a close encounter. Over time, the orbit could have stabilized into the configuration we see today. There is also a third possibility. Orcus and Vanth might have formed together during the collapse of a single region of material in the early solar system. In this case, they would not be a primary world and a captured moon, but rather a true binary system. Two objects forming side by side, two worlds born from the same cloud of ice and rock. In that scenario, the system may once have been even more dramatic than it appears today. Early gravitational interactions could have pushed the two bodies closer together, eventually settling into the stable orbit we observe now. At the moment, astronomers cannot say with certainty which of these possibilities is correct. Each explanation has strengths and weaknesses, and without direct exploration, the true history of the Orcus-Vanth system remains uncertain. But what we do know is that the presence of Vanth changes how we understand Orcus itself. Before the Moon was discovered, Orcus was simply another large Kuiper Belt object. After Vanth was identified, it became something more complex, a system, two worlds orbiting each other far beyond Neptune, their shared gravity shaping their motion, their mutual pull influencing their internal structure, and perhaps even affecting the evolution of their surfaces over billions of years. The discovery of Vanth also reminds us how incomplete our understanding of the outer solar system still is. Even today, new moons continue to be discovered around distant objects. Entire dwarf planet systems remain barely explored, and Orcus, despite being one of the larger bodies beyond Neptune, has never been visited by a spacecraft. Everything we know about this binary world comes from faint points of light collected by telescopes across millions of kilometers. Yet even those faint signals reveal something extraordinary. A dwarf planet, a large moon, a gravitational partnership formed in the deep cold of the Kuiper Belt, and together, Orcus and Vanth travel through space in quiet isolation, orbiting the Sun every 2.5 centuries, while locked in their own slow dance. But the mysteries of Orcus do not end with its moon, because the surface of this distant world may hold clues about something even more intriguing, hints that the dwarf planet's interior might once have been active, hints that its frozen crust could hide a more complicated past than anyone first imagined. And that story begins with the chemistry of its surface ice. If we could somehow travel billions of kilometers beyond Neptune and approach Orcus directly, the first thing we would notice is the light, or rather, the lack of it. At Orcus's distance from the Sun, sunlight is incredibly faint. The Sun itself would appear more like a bright star than a blazing disk. Daylight on the surface would resemble the dim glow of twilight on Earth. Yet even in this weak sunlight, Orcus reflects enough light for astronomers on Earth to study its surface composition. And those studies have revealed that the surface of Orcus is far from simple. Like many objects in the Kuiper Belt, Orcus is covered in ice. But these ices are not identical to the ice we know on Earth. In the deep cold of the outer solar system, temperatures remain close to minus 220 degrees Celsius. Under these conditions, substances that are gases or liquids near Earth become solid. Water freezes permanently. Methane freezes. Nitrogen freezes. Ammonia freezes. Entire landscapes in the outer solar system can be made from materials that would normally evaporate instantly near the Sun. By analyzing the light reflected from Orcus, astronomers had detected strong signatures of water ice on its surface. Water ice is one of the most common materials found in the Kuiper Belt. It forms the structural backbone of many icy dwarf planets and moons. But the water ice on Orcus is not just scattered randomly across the surface. Spectral observations suggest that large regions of Orcus may contain crystalline water ice. This detail is extremely important. Water ice can exist in two different structural forms: amorphous ice and crystalline ice. Amorphous ice forms when water freezes very quickly at extremely low temperatures, producing a disordered structure. This type of ice is common in the outer solar system, where temperatures are so cold that water molecules cannot easily rearrange themselves. Crystalline ice, on the other hand, forms when water molecules have enough energy to arrange themselves into an orderly lattice. But there is a problem. Radiation slowly destroys crystalline ice. Over time, energetic particles from space, cosmic rays and solar radiation, break apart the orderly crystal structure, converting it back into amorphous ice. In the Kuiper Belt, this process should occur over millions of years, which means something unusual must be happening on Orcus, because the presence of crystalline water ice suggests that the surface has been renewed or heated at some point in the past. Either the ice has been exposed relatively recently, or internal processes within Orcus once generated enough heat to transform the ice structure. Both possibilities raise fascinating questions. Could Orcus have experienced geological activity in the past? Could a warmer material from inside the dwarf planet have reached the surface? Or could impacts from other Kuiper Belt objects have excavated deeper layers of ice, exposing crystalline material that had been protected from radiation? At the moment, scientists are still investigating these possibilities. But water ice is only part of the story. Observations of Orcus's spectrum have also revealed hints of ammonia compounds on the surface. Ammonia is particularly interesting because it behaves differently from water ice under extreme cold. When mixed with water, ammonia can act as a kind of antifreeze, lowering the temperature at which ice melts. In the outer solar system, mixtures of water and ammonia can form ammonia hydrates, substances that may remain partially mobile, even at extremely low temperatures. If ammonia hydrates exist on Orcus, they could indicate that the dwarf planet once experienced cryovolcanism. Cryovolcanism is sometimes described as ice volcanism. Instead of molten rock erupting onto the surface, cryovolcanoes release mixtures of water, ammonia, methane, or other volatile compounds. These materials can flow or freeze across the surface, creating new terrain. Several worlds in the outer solar system show signs of cryovolcanic activity. Pluto itself displays evidence of such processes, as do some icy moons like Enceladus and Europa. Could Orcus have experienced similar activity? It is certainly possible. Even though Orcus is smaller than Pluto, its interior may once have contained enough heat to allow partial melting of ice deep below the surface. That heat could come from several sources. One source is radioactive decay within the rocky component of the dwarf planet's interior. Small amounts of radioactive elements trapped in the rock slowly release heat over time. Another source could be tidal interactions with Vanth, especially during the early stages of the Moon's orbital evolution. If Vanth once orbited closer to Orcus, gravitational forces might have flexed the interior of the dwarf planet, generating internal heat. Over millions of years, these processes could create pockets of warmer material beneath the surface. Eventually, some of that material might reach the surface through fractures in the icy crust. If this occurred, Orcus could have resurfaced itself with fresh ice in certain regions. That would explain the presence of crystalline water ice and ammonia compounds. But the surface of Orcus is also influenced by another powerful force, space weathering. The outer solar system is not a quiet place. Cosmic rays, solar radiation, and charged particles constantly bombard the surfaces of distant objects. Over extremely long timescales, these interactions alter the chemistry of surface materials. Complex organic compounds known as tholins can form through these radiation-driven reactions. Tholins are dark, reddish substances that accumulate on many Kuiper Belt objects. They are believed to be responsible for the deep red colors seen on some distant dwarf planets and icy bodies. Interestingly, Orcus does not appear strongly red compared to many other Kuiper Belt objects. Its surface color is more neutral. This suggests that either tholins are less abundant on Orcus, or that fresher ice exposures periodically refresh the surface. Another factor that may shape the surface is impact cratering. The Kuiper Belt contains countless small objects, and collisions have occurred throughout its history. Even though the region is vast, impacts still happen over geological timescales. When an object strikes Orcus, it could excavate deeper layers of ice and rock, exposing materials that had been buried for billions of years. Over time, these impacts could reshape the surface with craters, fractures, and ejecta deposits. Unfortunately, because Orcus is so distant, we have not yet seen detailed images of its terrain. Unlike Pluto, which was photographed up close by the New Horizons spacecraft in 2015, Orcus has never been visited by a probe. Its surface remains unresolved. From Earth's perspective, the dwarf planet still appears as a tiny disk of light, too small and too far away for even the most powerful telescopes to reveal its landscape. Yet the clues hidden in its reflected light tell us something remarkable. Orcus is not simply a frozen, unchanging ball of ice drifting through space. Its surface chemistry hints at a history of transformation. Water ice, ammonia compounds, possible resurfacing events, perhaps even ancient cryovolcanic activity. All of these pieces suggest that Orcus may once have been more dynamic than its quiet appearance would suggest. And if the surface has been altered by internal processes, then the real story of Orcus may lie deeper within the dwarf planet itself, beneath the frozen crust, beneath the silent ice plains, inside a hidden interior that may still hold the remnants of ancient heat from the earliest days of the solar system. From billions of kilometers away, Orcus looks quiet, a frozen dwarf planet drifting slowly through the darkness of the Kuiper Belt. Its surface reflects faint sunlight. Its moon circles it in silence. Nothing about its appearance suggests activity or motion. But appearances can be deceptive in the outer solar system. Many worlds that once seemed frozen and lifeless have turned out to hide complex internal structures beneath their icy crusts. Pluto, once believed to be geologically dead, revealed glaciers, mountains, and possible cryovolcanic domes when the New Horizons spacecraft passed by in 2015. Even small icy moons like Enceladus and Europa have surprised scientists with hidden oceans and internal heat. So the question naturally arises, could Orcus also hide something beneath its frozen surface? To answer that, astronomers begin with a simple principle: density. The density of a world tells us what it might be made of inside. Measurements of the Orcus-Vanth system suggest that Orcus has a density somewhere around 1.5 grams per cubic centimeter. That number places it between pure water, ice, and solid rock. This means Orcus is almost certainly a mixture, part ice, part rock. This combination is extremely common among dwarf planets in the outer solar system. During the early formation of the solar system, dust grains and icy particles gradually stuck together, forming larger and larger bodies. These building blocks naturally contained both rocky minerals and frozen volatile compounds. Over time, gravity pulled these materials into growing worlds. But once a world becomes large enough, something important begins to happen inside it: differentiation. Differentiation occurs when the interior of a body separates into layers. Heavier materials sink toward the center. Lighter materials rise toward the surface. On Earth, this process created a dense metallic core surrounded by a rocky mantle and crust. On icy dwarf planets like Orcus, the structure would be different but still layered. Deep inside Orcus, there may be a rocky core made of silicate minerals and heavier elements. Surrounding that core could be a thick mantle of water ice mixed with other frozen compounds. Above that mantle lies the outer crust we observe today. But for differentiation to occur, something must provide energy, heat. Even in the distant cold of the Kuiper Belt, heat can be generated within a young world. One major source is radioactive decay. When Orcus formed billions of years ago, its rocky material likely contains small amounts of radioactive elements, such as uranium, thorium, and potassium. As these elements slowly decayed, they released heat into the surrounding rock. Over millions of years, this heat could build up inside the dwarf planet. Another possible source of heat comes from the formation process itself. As Orcus accumulated mass during its early growth, gravitational energy from impacts and compression would have warmed its interior. Together, these heat sources may have raised the internal temperature enough to partially melt some of the ice within the dwarf planet. And when water ice melts, especially when mixed with substances like ammonia, it can form liquid reservoirs beneath the surface. This possibility has led scientists to consider an intriguing idea. At some point in its history, Orcus may have possessed a subsurface ocean, not an ocean like those on Earth, not waves or storms, but a hidden layer of liquid water mixed with ammonia trapped beneath kilometers of frozen crust. Such an ocean would likely have existed only temporarily. Over time, as the internal heat sources weakened, the liquid layer would slowly freeze again. But even a temporary ocean could have profound effects on the dwarf planet. As liquid water froze, it would expand slightly, creating internal pressure. That pressure could fracture the outer crust, allowing new material to reach the surface. This process might explain why some of the ice observed on Orcus appears relatively fresh. It might also explain the presence of ammonia compounds, which could have been transported upward during episodes of cryovolcanic activity. But internal oceans are not the only possible hidden feature. The interior of Orcus could also contain complex mixtures of ice layers. Different types of ice form under different temperatures and pressures. Water ice alone has multiple crystal structures, some denser than others. Deep within an icy body, these different phases can form stacked layers, each with unique properties. These layers could affect how heat moves through the interior. They could influence the long-term evolution of the dwarf planet, and they might even affect how the crust responds to impacts or gravitational forces from Vanth. Speaking of Vanth, the Moon itself may have played a role in Orcus's internal evolution. Gravitational interactions between two orbiting bodies can generate internal heat through tidal forces. When a moon orbits close to its parent body, the gravitational pull stretches and compresses the interior repeatedly. This flexing creates friction inside the object, generating heat. On Jupiter's moon Io, tidal heating produces intense volcanic activity. On Europa, it helps maintain a global ocean beneath the icy surface. Orcus and Vanth are not close enough to produce such dramatic effects today, but earlier in their history, the Moon's orbit may have been different. If Vanth once orbited closer to Orcus, tidal forces could have been stronger, adding extra heat to the dwarf planet's interior. Over time, as the orbit stabilized, the tidal heating would have weakened. But the early effects may still be recorded in Orcus's internal structure. Even today, subtle clues about that internal structure may appear on the surface. Surface fractures, possible cryovolcanic deposits, chemical signatures of subsurface material. Unfortunately, until the spacecraft visits Orcus, we cannot see these features directly. The dwarf planet remains unresolved in our telescopes. Its interior is hidden. Its surface is distant. Its secrets are inferred from faint traces of reflected sunlight. Yet the possibility of internal complexity transforms our understanding of Orcus. Instead of a simple frozen object, we see a world that may once have been geologically active, a world where internal heat slowly reshaped the crust, a world where buried layers of ice and rock evolved over billions of years. And if Orcus truly experienced such internal processes, then it becomes more than just another Kuiper Belt object. It becomes a laboratory for studying how distant icy worlds evolve. But Orcus does not exist alone in this distant region of the solar system. It is surrounded by countless other icy bodies, fragments of the same ancient disk from which it formed. To fully understand Orcus, we must zoom out even farther, beyond the dwarf planet, beyond its moon, and into the vast frozen region known as the Kuiper Belt, where Orcus has spent billions of years traveling through deep space. To truly understand Orcus, we have to step far away from it, not just a few thousand kilometers, not even a few million. We must zoom out far enough to see the entire region of space where Orcus lives, because Orcus is not an isolated object. It is part of one of the most fascinating regions of our solar system, the Kuiper Belt. The Kuiper Belt begins just beyond the orbit of Neptune, roughly 30 astronomical units from the Sun, and stretches outward for tens of billions of kilometers. It is an enormous ring of icy objects surrounding the outer solar system. For most of human history, astronomers had no idea this region even existed. The solar system was believed to end with Neptune. Pluto, discovered in 1930, was thought to be a strange and lonely outlier. But in the early 1990s, that view changed completely. In 1992, astronomers discovered the first object beyond Pluto that clearly belonged to a new population of distant icy bodies. That object was called 1992 QB1. And once astronomers knew where to look, they began finding many more. Soon it became clear that Pluto was not alone at all. Instead, it was one of thousands of objects orbiting in a vast outer belt of frozen remnants left over from the formation of the solar system. This region was named after the astronomer Gerard Kuiper, who had predicted the possibility of such a distant reservoir decades earlier. Today, we know that the Kuiper Belt contains millions of objects. Some are only a few kilometers across. Others are hundreds of kilometers wide. A few are large enough to be classified as dwarf planets. Pluto is one. Eris is another. Haumea and Makemake belong to this group as well. And Orcus is one of the most significant members of this distant family. These objects are often described as time capsules. They formed more than 4.5 billion years ago, during the earliest stages of planetary formation. In the inner solar system, planets grew rapidly and cleared away most of the leftover debris. But far from the Sun, growth was slower. Many objects never became full planets. Instead, they remained as frozen building blocks from the birth of the solar system. The Kuiper Belt preserves these ancient bodies almost exactly as they formed. And because Orcus is one of the larger objects in this region, studying it helps scientists understand what the early solar system was like before the planets settled into their current arrangement. But the Kuiper Belt is not a quiet place. It is structured and shaped by gravity. And the most important influence in that region is Neptune. Neptune acts like a gravitational sculptor. Its powerful gravity affects the orbits of objects throughout the Kuiper Belt, creating patterns that astronomers can observe today. Some objects have been scattered outward by Neptune's gravity. Others have been pushed into tilted or elongated orbits. But some objects became trapped in special orbital resonances with Neptune. These resonances occur when an object's orbital period forms a precise ratio with Neptune's orbit. For example, Pluto completes 2 orbits around the Sun in the same time that Neptune completes 3. This 2-to-3 resonance protects Pluto from close encounters with Neptune, and Orcus shares that exact same resonance. Objects in this resonance are called Plutinos. They move through space in synchronized patterns with Neptune's gravity, ensuring that their orbits remain stable even though they cross Neptune's orbital distance. This is one reason Orcus has survived for billions of years without being ejected from the solar system. Its orbit is protected by the same gravitational rhythm that stabilizes Pluto. But the Kuiper Belt is not uniform. Astronomers divide it into several different populations based on how objects move. Some objects belong to the classical Kuiper Belt, where their orbits remain relatively circular and stable. Others belong to the scattered disk, where their orbits are stretched and chaotic due to gravitational encounters with Neptune. And still others belong to resonance groups like the Plutinos. Each population tells a story about how the solar system evolved. The presence of resonant objects like Orcus is particularly important because it provides evidence that the giant planets migrated early in their history. When the solar system first formed, the giant planets likely did not occupy their current positions. Instead, they slowly moved outward or inward as they interacted with a massive disk of leftover planet-forming material. Neptune's outward migration is believed to have reshaped the entire outer solar system. As it moved, it captured objects into resonances and scattered others outward into distant regions. This process helped create the structure of the Kuiper Belt we see today. In other words, Orcus's orbit is not just a curiosity. It is a record of a dramatic period in the solar system's past, a time when the giant planets were shifting positions, a time when countless icy worlds were being pushed, captured, and scattered across space. And Orcus survived that chaos. It remained trapped in a stable orbit, protected by Neptune's gravitational resonance. And because it remained stable, Orcus preserved information about the early solar system that scientists are only now beginning to decode. But the Kuiper Belt holds another mystery as well. Many of its largest objects, including Orcus, have moons. Pluto has several. Eris has one. Haumea has two. And Orcus has Vanth. The existence of these moons suggests that collisions between large icy bodies were once common in the outer solar system. These collisions may have reshaped many of the worlds we see today. They may have created moons. They may have altered surfaces. They may even have changed internal structures. The Kuiper Belt, therefore, is not just a quiet region of frozen debris. It is a dynamic environment that has experienced billions of years of collisions, gravitational interactions, and slow orbital evolution. And within this vast region, Orcus continues its journey, completing one orbit around the Sun every 247 years, traveling billions of kilometers through space, accompanied by its moon Vanth, part of a distant population of ancient worlds that still hold the memory of how the solar system was born. But Orcus may not only be a survivor of the solar system's early chaos, it may also be a product of that chaos. Because the next question scientists ask is not just where Orcus is today, but how it formed in the first place. And that story takes us back to the violent early era, when the building blocks of planets were still colliding across the young solar system. Billions of years ago, long before the planets settled into the stable orbits we see today, the solar system was a violent and chaotic place. There were no clear planetary boundaries, no calm gravitational order. Instead, a vast rotating disk of gas, dust, rock, and ice surrounded the young sun. This structure is known as the protoplanetary disk, and it was from this disk that every planet, moon, asteroid, and comet eventually formed. Near the sun, temperatures were extremely high. Only rocky materials and metals could survive in solid form. This is why the inner planets, Mercury, Venus, Earth, and Mars, are primarily composed of rock and metal. But farther away from the sun, the environment was completely different. Beyond what scientists call the frost line, temperatures dropped low enough for volatile compounds to freeze. Water became solid ice. Methane froze. Ammonia froze. Even nitrogen could exist as solid frost. In this cold outer region of the disk, icy grains began sticking together. At first, they formed microscopic clusters, then pebble-sized fragments, then kilometer-sized objects called planetesimals. These planetesimals were the fundamental building blocks of the outer solar system. Through countless collisions and gravitational interactions, some of these bodies gradually grew larger. Some became hundreds of kilometers wide. Some reached dwarf planet size. A few eventually became the massive cores of the giant planets. Orcus likely began its life as one of these icy planetesimals. Somewhere in the distant outer disk, small particles of ice and rock slowly accumulated under the influence of gravity. Over time, the growing body attracted more material, sweeping up debris from its surrounding region. The process was slow. far slower than planet formation in the inner solar system. Out beyond Neptune, the density of material in the protoplanetary disk was much lower. Collisions occurred less frequently, and objects took longer to grow. This is one reason the Kuiper Belt still contains so many small bodies today. The process of planetary growth never fully completed in that region. Orcus represents one of the largest survivors of that incomplete formation process. But the growth of Orcus did not occur in a peaceful environment. As planetesimals grew larger, their gravity began pulling objects toward them. Collisions became more energetic. Some impacts shattered bodies into fragments. Others merged them into larger worlds. These early collisions were capable of dramatically altering the shapes and internal structures of growing objects. Orcus may have experienced several such collisions during its formation. Some of those impacts may have delivered additional rock and ice to its interior. Others may have stripped away material or reshaped its surface. One especially important collision may have played a role in creating its moon, Vanth. Many astronomers suspect that Vanth could have formed after a massive impact involving Orcus and another large Kuiper Belt object. In this scenario, the collision would have ejected a cloud of debris into orbit around the dwarf planet. Over time, that debris could have gathered together through gravity, forming the moon we observe today. This type of event is believed to have formed several major moons in the solar system, including Earth's moon and Pluto's moon Charon. But Orcus formed during an even more dramatic period in solar system history, a time when the giant planets themselves were still migrating. In the early solar system, Jupiter, Saturn, Uranus, and Neptune did not necessarily occupy their current positions. Computer simulations suggest that the giant planets gradually shifted their orbits as they interacted with the surrounding disk of planetesimals. This planetary migration had enormous consequences. As Neptune moved outward from the Sun, its powerful gravity disturbed the orbits of countless objects in the outer disk. Some were pushed into new regions of space. Some were thrown into extremely elongated orbits. Some were completely ejected from the solar system, but others were captured into stable resonances. Objects like Pluto and Orcus became trapped in gravitational patterns where Neptune's orbital period and their own periods formed stable ratios. These resonances protected them from close encounters with Neptune. And once captured, they could remain stable for billions of years. This process explains why Orcus today shares the same 2 to 3 orbital resonance as Pluto. But it may also explain the unusual symmetry between their orbits. When Neptune migrated outward, it may have captured objects into resonant positions on opposite sides of the solar system. Pluto settled into one of those positions. Orcus settled into another. The result was a mirrored orbital configuration that has persisted ever since. This history means that Orcus is not just a relic from planetary formation. It is also a survivor of planetary migration, a witness to one of the most dramatic periods in the solar system's evolution. But the formation story does not end with Neptune's migration. The Kuiper Belt itself continued evolving long after the planet stabilized. Collisions between objects still occurred. Some bodies fragmented into smaller pieces. Others merged to form larger dwarf planets. During these collisions, surface materials were constantly reshaped. Impact craters formed. Debris blankets spread across icy terrain. fragments of ice and rock were redistributed across surfaces. Orcus's surface today likely records the scars of billions of years of impacts. Unfortunately, because Orcus is so distant, we cannot yet see these craters directly. But based on what we know about similar worlds, its surface may contain ancient impact basins formed during the early bombardment era. It may also contain fractures caused by internal stresses, and perhaps regions where fresh ice once flowed onto the surface from below. These features would tell the story of Orcus's evolution, a story beginning in the dusty chaos of the proto-planetary disk, continuing through violent collisions, shaped by Neptune's migration, and preserved in the quiet darkness of the Kuiper Belt. Yet even after billions of years, Orcus still follows the same slow orbit around the Sun. Every 247 years, it completes one full journey. Every orbit carries it through the same distant region of space where it formed long ago. It continues to travel alongside thousands of other icy worlds, some smaller, some larger, some still undiscovered. And as astronomers search deeper into the Kuiper Belt, they are beginning to realize that Orcus is not simply one object among many. It is part of a much larger family of dwarf planets that share surprising similarities. But how similar is Orcus to Pluto itself? Are they truly twins? Or does Orcus hide differences that make it unique among the worlds beyond Neptune? Answering that question requires a direct comparison between these two distant dwarf planets, two worlds linked by gravity, but separated by billions of kilometers of space. When Orcus was first discovered, astronomers quickly noticed the strange connection between its orbit and Pluto's. The two objects share the same resonance with Neptune, and their paths through the solar system appear almost like mirror reflections of one another. Because of this unusual relationship, Orcus is often described as Pluto's twin. But when scientists look closer, the similarities begin to fade. Orcus and Pluto may share an orbital rhythm, but physically, they are very different worlds. The most obvious difference is size. Pluto is one of the largest known objects in the Kuiper Belt. Its diameter measures about 2,377 kilometers, making it more than twice the size of Orcus. Orcus, by comparison, measures roughly 900 kilometers across. That means Pluto's volume is dramatically larger. It contains far more mass, and its gravity is significantly stronger. This difference in gravity has important consequences. On Pluto, stronger gravity allows the surface to hold volatile ices like nitrogen, methane, and carbon monoxide. These materials form glaciers and plains that can slowly move across Pluto's surface. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more complex than anyone expected. Pluto has towering mountains of water ice, smooth plains of nitrogen ice, enormous impact basins, and even evidence of possible cryovolcanoes. In contrast, Orcus is probably too small to retain large amounts of nitrogen or methane on its surface for billions of years. Those lighter compounds would slowly escape into space over time. Instead, Orcus is thought to be dominated by water ice and possibly ammonia compounds, which are heavier and more stable in the deep cold of the Kuiper Belt. But even though Orcus is smaller, the comparison with Pluto becomes interesting when we examine their moons. Pluto has several moons. the largest of which is Charon. Charon is so large compared to Pluto that the two objects form a binary dwarf planet system. Their shared center of gravity actually lies outside Pluto itself, meaning both bodies orbit a point in space between them. The Orcus system appears somewhat similar. Its moon Vanth is unusually large compared to the size of Orcus. Although Vanth is smaller than Charon relative to its primary, the Orcus-Vanth pair may still behave like a partially binary system. Both pairs, therefore, share a similar structural feature, a dwarf planet accompanied by a large moon that plays a major role in the system's gravitational dynamics. But when astronomers compare Orcus not only with Pluto, but with other dwarf planets, a much broader picture begins to emerge. The Kuiper Belt contains several known dwarf planets, each with its own unique characteristics. Eris, for example, is slightly larger than Pluto and far more distant from the Sun. It travels on a highly elongated orbit that takes it deep into the scattered disk, far beyond the main Kuiper Belt. Eris is extremely reflective, covered with bright methane ice that gives it one of the highest albedos in the solar system. Then there is Haumea, one of the strangest dwarf planets ever discovered. Haumea rotates incredibly fast, completing one full rotation in less than 4 hours. That rapid spin has stretched it into an elongated shape, almost like a cosmic football. Its surface is covered with nearly pure water ice, and it possesses 2 moons as well as a thin ring system. Another dwarf planet, Makemake, is somewhat closer to Pluto in size, but has a very different surface chemistry. Makemake's surface appears rich in methane ice and other volatile compounds, giving it a reddish coloration. Compared with these worlds, Orcus seems almost modest. It does not spin as rapidly as Haumea. It is not as massive as Eris. It does not possess the complex nitrogen glaciers seen on Pluto. Yet Orcus remains extremely important scientifically. Its intermediate size places it at a critical boundary in planetary evolution, large enough to become spherical, large enough to retain a moon, large enough to develop a differentiated interior, but small enough that some processes, such as long-lasting volatile atmospheres, may never have occurred there. This makes Orcus an important transitional object. It helps scientists understand what happens when icy bodies grow large enough to become dwarf planets, but not large enough to become fully complex worlds like Pluto. In many ways, Orcus may represent a middle step in the evolution of outer solar system bodies, larger than most Kuiper Belt objects, smaller than the most dominant dwarf planets, and that intermediate size could help explain some of its unusual features. For example, the possible presence of ammonia compounds on its surface suggests that Orcus may have experienced limited internal activity in the past, but its smaller size means that any internal heat would likely have dissipated more quickly than on Pluto. If Orcus once possessed a subsurface ocean, it may have frozen solid billions of years ago. Pluto, on the other hand, may still possess a liquid ocean beneath its icy crust, even today. These differences help scientists understand how internal heat evolves in icy worlds of different sizes. Another interesting comparison involves surface color. Many Kuiper Belt objects appear deep red due to the accumulation of radiation-processed organic materials called tholins. Pluto has reddish regions as well, but Orcus appears somewhat more neutral in color. This suggests that its surface chemistry may differ from many other Kuiper Belt bodies. Perhaps fresh ice has been exposed more recently, or perhaps the original composition of Orcus formed under slightly different conditions in the early solar system. But the comparison between Orcus and Pluto goes beyond physical characteristics. Their orbital relationship remains one of the most intriguing features of the outer solar system. Both are trapped in the same gravitational resonance with Neptune. Both complete nearly identical orbital periods, and yet their positions are offset in such a way that they rarely occupy the same region of space. It is almost as if the solar system created two versions of the same orbital pattern, one filled by Pluto, one filled by Orcus. This strange symmetry has fascinated astronomers for decades, and it highlights how the gravitational architecture of the solar system can produce elegant patterns that persist for billions of years. Yet despite these similarities and comparisons, Orcus still remains largely mysterious. Unlike Pluto, no spacecraft has ever visited it. We have no close-up images of its terrain. We do not know whether its surface contains enormous basins, towering ice cliffs, or smooth plains of frozen material. Everything we know comes from distant observations made from Earth and from telescopes in orbit. That means Orcus still has the power to surprise us. Because when a spacecraft finally does travel to this distant world, if such a mission is ever launched, it may reveal landscapes and geological features no one expects, just as Pluto did, just as many other distant worlds have done. And until that day arrives, Orcus remains one of the great unexplored worlds of the outer solar system, a dwarf planet with a large moon, a twin of Pluto in orbital rhythm, a survivor of planetary migration, and a frozen relic from the earliest era of our cosmic neighborhood. But there is still one final question left to explore, not about the past of Orcus, but about its future, because one day humanity may send a spacecraft across the vast darkness of the Kuiper Belt to finally see this distant world up close. And when that happens, Orcus may reveal secrets that will change how we understand the outer solar system forever. For now, Orcus remains one of the most distant worlds humanity has ever studied. Every piece of information we have about it, its size, its orbit, the presence of water ice, even the discovery of its moon Vanth, has come from faint points of light captured by telescopes millions or billions of kilometers away. No spacecraft has ever approached it. No probe has ever photographed its surface. No instrument has ever measured its terrain, its gravity field, or the detailed chemistry of its crust. Compared to the planets and moons closer to the Sun, Orcus is still a mystery. And yet, that mystery is exactly what makes it so fascinating. Because history has shown that the first close look at a distant world often changes everything. For decades, Pluto was little more than a tiny dot of light in telescope images. Scientists knew its orbit and its approximate size, but almost nothing about its surface. Then, in 2015, the spacecraft New Horizons flew past Pluto for the first time. The images it returned stunned the world. Instead of a frozen, inactive relic, Pluto turned out to be a geologically complex planet. It had mountains made of water ice rising several kilometers high. It had smooth plains of nitrogen ice slowly flowing like glaciers. It had enormous basins, fractured terrain, and possible cryovolcanoes. Everything scientists thought they knew about Pluto had to be reconsidered. And Orcus could one day produce the same kind of surprise. Because based on what we already know, Orcus may possess several features that could only be fully understood through direct exploration. For example, its surface composition hints at crystalline water ice and ammonia compounds. These materials suggest that Orcus may have experienced some form of internal activity in the past. If a spacecraft were to fly past Orcus, it could search for geological evidence of that activity. Are there large cryovolcanic flows frozen across the surface? Are there fractures where material once erupted from the interior? Are there impact basins exposing deeper layers of ice and rock? Only direct imaging could answer those questions. Another mystery involves the moon Vanth. From Earth, Vanth appears as a faint companion orbiting Orcus roughly every 9.5 days. But we know very little about its surface, its shape, or its internal structure. A spacecraft could reveal whether Vanth formed from a massive collision, as Charon likely did with Pluto, or whether it was captured from elsewhere in the Kuiper Belt. Detailed images might show whether Vanth's surface resembles Orcus, or whether it is chemically and geologically distinct. That comparison alone could reveal the history of the entire system. But exploring Orcus would not be easy. The Kuiper Belt lies incredibly far away. Even traveling at the tremendous speeds of interplanetary spacecraft, a mission to Orcus would require many years, possibly decades, just to reach its destination. To understand the scale of this challenge, consider the journey of New Horizons. Launched in 2006, the spacecraft traveled at more than 50,000 kilometers per hour, becoming one of the fastest probes ever sent into space. Yet it still took 9.5 years to reach Pluto. Orcus lies at a similar distance from the Sun. A mission to Orcus would therefore require a comparable journey. Such missions demand careful planning, long-term funding, and technology capable of operating far from the Sun, where solar energy becomes extremely weak. Instead of solar panels, spacecraft traveling to the Kuiper Belt typically rely on radioisotope thermoelectric generators, devices that produce electricity from the heat released by radioactive decay. These power sources allow spacecraft to operate even in the deep darkness beyond Neptune. Despite the challenges, scientists have already begun discussing future missions to Kuiper Belt objects. Exploring these distant worlds helps answer some of the most important questions about the formation of the solar system. The Kuiper Belt contains objects that have remained relatively unchanged for billions of years. They preserve the chemical and structural conditions that existed when the planets first formed. By studying these ancient bodies, scientists can learn how planets grew, how the giant planets migrated, and how the architecture of the solar system evolved over time. Orcus is particularly valuable because it sits at the intersection of several important categories. It is large enough to be considered a dwarf planet. It has a large moon, forming a gravitational system that can reveal clues about its mass and internal structure. And it shares an orbital resonance with Pluto, providing evidence of Neptune's migration during the early history of the solar system. A spacecraft mission to Orcus could therefore address multiple scientific goals at once. It could study the geology of an intermediate-sized dwarf planet. It could analyze the chemistry of Kuiper Belt surface materials. It could examine the formation of binary systems in the outer solar system. And it could compare Orcus directly with Pluto, helping scientists understand why some dwarf planets evolve into complex worlds while others remain relatively simple. Even without a spacecraft, new telescopes are already beginning to improve our understanding of distant objects like Orcus. Space telescopes, such as the James Webb Space Telescope, allow astronomers to analyze the infrared light reflected from distant worlds with unprecedented precision. These observations can reveal the presence of specific molecules on their surfaces. Future observatories, including extremely large ground-based telescopes currently under construction, will be capable of resolving distant objects with greater detail than ever before. Although they may not show individual craters or mountains, they will provide far more accurate measurements of size, reflectivity, and surface composition. Every new observation helps refine our understanding of Orcus. Yet even with the most powerful telescopes, there will always be limits. A world billions of kilometers away cannot fully reveal its secrets through reflected light alone. To truly understand Orcus, we would eventually need to send a spacecraft, a probe that could fly past the dwarf planet, capture high-resolution images of its terrain, measure its gravity field, and analyze the chemistry of its surface. Such a mission would take patience. It would require years of travel, but the reward could be extraordinary, because somewhere in the dark outer reaches of the solar system, Orcus continues its slow journey around the Sun, a frozen dwarf planet orbiting once every 247 years, accompanied by its mysterious moon Vanth. Part of the ancient population of icy worlds left behind from the birth of the solar system. For billions of years, it has remained unchanged, drifting quietly through the Kuiper Belt. But someday, perhaps in the not-too-distant future, a spacecraft may finally arrive there. And when it does, the quiet world we now know only as a distant point of light may suddenly become something far more real. A landscape, a place, another chapter in the unfolding story of our solar system. Until then, Orcus remains what it has always been. Pluto's strange twin, traveling through deep space, waiting to be explored.